When the facts bend reality, this is beyond plausible.
You are walking across the vast, dry plains under the scorching sun in southwestern Queensland. If you see a shiny black head of a snake emerging from cracks in the ground, then be sure to avoid this creature at all costs and as quickly as possible. Its name is the inland taipan. It may not threaten you like a cobra or rattlesnake, but it is actually the most venomous and dangerous snake in the world. According to the ranking of lethal toxicity, its venom is 7 times more dangerous than that of the sea snake, 23 times more than the Indian cobra, and 72 times more than the venom of the king cobra. On average, the king cobra bite releases 420 milligrams of venom, enough to kill about 2,600 mice. A bite from a taipan only secretes about 44 milligrams of venom. However, that tiny amount of venom is enough to kill up to 220,000 mice. And in some special cases, this snake has been recorded to inject more than 110 milligrams of venom in a single bite. An amount of venom sufficient to kill 500,000 mice or more than 100 adult humans. Just a light snap from a taipan can cause permanent damage. And if a specialized anti-venom serum is not injected within 45 minutes, the victim's wound will bleed continuously. The kidneys will stop functioning, the entire body becomes paralyzed, the lungs fail, and ultimately lead to death. Before people discovered the anti-venom for this snake, every bite from an inland taipan was almost certainly fatal. But why is the bite of this snake so deadly? What mechanism does its venom use to cause damage to human body parts? How did it evolve to possess the most dangerous venom in the world? This is a video about the venom of one of Australia's most dangerous animals, the inland taipan. To understand why the taipan is so dangerous, we first need to determine the origin of venom that appeared early in the evolutionary program. Like many other predatory traits of animals, snake venom emerged due to sudden geographical and habitat changes over millions of years. However, that does not explain how and when their venom appeared. Researchers speculate that the venom of all snake families likely originated from a single common source about 170 million years ago. Therefore, the toxicity in reptile venom is very diverse, and their evolutionary pathways occurred independently through many different routes. So we cannot know exactly when this evolutionary event occurred. Researchers often look for traces of evolution in the fossil record. They believe the first snakes caught and killed prey by constriction, similar to how snakes still do today. Their ancestors possessed short and sturdy vertebrae, along with strong, flexible muscles located at the contact points between vertebrae, allowing the spine to have the ability to bend at many positions on the body. A snake would kill its captured prey by tightly coiling its body around the animal. When the muscle fibers contract to shorten the distance between vertebrae, the squeezing force it generates is strong enough to restrict blood flow in the prey's body to vital organs like the brain and heart. This leads to unconsciousness and ultimately a painful death from cardiac arrest. The forested habitat of the Jurassic period was very suitable for this hunting style, where a snake could coil and hide in dense bushes, patiently waiting for prey to pass by, then suddenly strike out, grab, and tightly coil around the prey. Finally, it squeezes the victim tightly until death. The connection between how snakes hunt and their habitat remains unchanged to this day. We still often encounter snakes coiled up in forests or in very open places, because these habitats are ideal for ambushing prey. But when the Miocene epoch occurred from about 23 to 6 million years ago, it was a rather difficult period. That time was not very favorable for the snake's hunting tactics. During this period, the planet's climate underwent a slow process of change. The air gradually became colder and drier, creating favorable conditions for the development of savanna grassland terrains. This is the ideal living environment for rodents and birds, but it proved unsuitable for snakes. Because the ambush hunting mechanism and squeezing prey to death are not suitable here, where the hunter must chase its target in open spaces. This requires muscles with a longer and more flexible structure, rather than short muscles that can only generate strong squeezing force. Therefore, if a snake wants to catch up with its prey, it needs something else to paralyze or even completely eliminate the target. Over millions of years of evolution, snake venom has developed into a complex biological toxin compound, capable of preventing prey from escaping by killing them on the spot. Most of the venom in bites far exceeds the amount necessary to kill an animal. But why does snake venom need to be so highly toxic? Actually, venom serves many different functions. First, it will prevent the prey from escaping the area. Next, when the toxin enters the bloodstream, the organs will become paralyzed. This will help prevent the prey from fighting back, while the snake is swallowing its prey. Additionally, the venom helps accelerate the digestion process by breaking down nutrients from the prey. One astonishing fact about snake venom is that it has evolved not only to be extremely toxic to prey but also to be highly diverse in types. The black mamba originates from Africa, while the coastal taipan originates from Australia. Both belong to the Elapidae family, sharing many similarities in size, color, and venom. They both hunt small mammals such as rats and mice. However, the biological components in their venoms are very different. The venom of the black mamba primarily contains Kunitz peptides and alpha neurotoxins. In contrast, the venom of the coastal taipan is mainly composed of beta neurotoxins and phospholipases. It operates through a completely different mechanism than alpha neurotoxins. We will explore the workings of these toxins in detail later. But the above example is a clear illustration of convergent evolution. The venoms of these two species share the same purpose of killing prey, yet their compositions are very different. Many major and minor variations in venom composition have been found among similar snake species worldwide. In Australia, there are 3 species of taipan, primarily distributed in the mountainous regions of the country's west. The coastal taipan has 2 subspecies found along the eastern coast of Australia and the southern border of Papua New Guinea. The inland taipan is found in a remote area of western Queensland. Their diets consist of mammals of similar sizes. Despite many shared characteristics, their venom compositions differ significantly. The venom of the coastal taipan mainly contains beta neurotoxins and phospholipases. The inland taipan possesses both alpha neurotoxins and beta phospholipase toxins. It is difficult to pinpoint exactly why taipans developed such potent venom. It may be due to the scarcity and difficulty of hunting prey in the remote areas they inhabit. But this could also result from random genetic mutations not selected in any way we currently understand. Despite possessing potent venom capable of killing prey with a single bite, the inland taipan often bites its prey multiple times in succession. This allows the venom to spread throughout the body. The process unfolds as follows. First, it injects a mixture of toxic proteins into the blood and subcutaneous fat. This mixture begins to act immediately. One enzyme breaks down proteins in the victim's blood and blood vessels, loosening connective tissue, weakening vessel walls, and causing internal organ inflammation. Simultaneously, another enzyme accelerates the absorption and spread of the venom, bringing death to the victim more quickly. What truly kills the bitten organism are hemotoxins. Taipan venom contains proteins that cause immediate blood clotting. It makes the blood clot like jelly. However, instead of clotting the blood throughout the entire body, the opposite occurs. Thousands of small clots accumulate right at the bite site, blocking new blood flow and causing it to leak out. This can be fatal due to severe blood loss. The next most affected organ is the kidneys. They are directly damaged by exposure to certain proteins in the venom, or indirectly harmed by toxins affecting metabolic processes. Myotoxins specifically target muscle fibers, causing muscle tissue damage and release into the bloodstream. At this point, the kidneys begin working to remove the damaged tissues. But myoglobin from the muscle fibers is toxic to the kidneys, impairing their complex filtration system, ultimately leading to severe organ destruction. Additionally, dying muscles absorb large amounts of fluid from the blood, causing the body to go into shock. Assuming, by some miracle, the poisoned organism survives blood loss and kidney failure, it can hardly survive the effects of neurotoxins. These are the proteins primarily responsible for this snake's terrifying lethality. As known, the inland taipan possesses both alpha and beta neurotoxins simultaneously. The alpha neurotoxins in the inland taipan's venom are fast-acting lethal proteins, targeting acetylcholine receptors directly at the neuromuscular junction. Acetylcholine is a crucial compound in neural signal transmission, allowing the brain to communicate with muscles and control muscle fiber contraction and relaxation. When alpha neurotoxins bind to these receptors, they prevent acetylcholine from functioning. The result is a halt in communication between the brain and muscles, leading to rapid muscle paralysis. This sounds dangerous, but modern medicine can easily neutralize this process. By reversing the toxins binding to the receptor. If someone is bitten and experiences paralysis caused by these toxins, rest assured, as the victim can be completely saved with antivenom, provided it is administered within 30 minutes of the bite. But things are not so simple with the other neurotoxins in the inland taipan's venom. Beta neurotoxins act more slowly but have a much higher fatality rate. Beta pyridoxine constitutes the main component of the inland taipan's venom. It is part of preprotein enzymes found naturally in cells. Normally, their activity and concentration are very carefully controlled, because if uncontrolled, they can have dangerous effects on the cellular machinery. Pyridoxine primarily interacts with components of the cellular network. Specifically, it targets the chemical bond in the fatty acid chain with the glycerol molecule in phospholipids. Pyridoxine will break this bond. That alone is enough to cause significant damage by disrupting the cellular network. But the product of this reaction is what truly causes the biggest problem. When phospholipids are broken down, they release a fatty acid chain, particularly arachidonic acid. This leads to permanent paralysis and death for the victim. Like alpha neurotoxins, pyridoxine's site of action is the neuromuscular junction. That is the point of communication between the nervous system and muscles. If paradoxin enters the presynaptic cell, it begins breaking down phospholipids to produce arachidonic acid. Subsequently, a flood of calcium ions is released. Cells are very sensitive to changes in the quantity of a specific ion, and a large increase in calcium ion concentration causes nearly all acetylcholine to be released from the synapse. They move away from the site, bind to receptors, then become oversensitive and self-deactivate in a short time. This is not strong enough to cause paralysis, but by now, almost all acetylcholine has been used up. And even if the cell wants to produce more, it cannot, because arachidonic acid also blocks the reuptake of choline, a molecule necessary to produce acetylcholine. But this is not the only problem caused by paradoxin. A more dangerous situation occurs if it enters the area behind the synaptic junction. Acetylcholine receptors can be completely deactivated once again. Acids are again broken down into arachidonic acid, causing a massive release of calcium ions. This time, calcium activates enzymes that deactivate acetylcholine receptors, even causing them to be removed from the cellular network within just a few hours. The result is the complete and irreversible shutdown of the synapses. Therefore, the brain cannot directly control the muscles. When the body is completely paralyzed, the lungs cannot function. The heart stops beating, and the victim will die from respiratory failure. There are many types of beta neurotoxins found in various snake venoms, but paradoxin is the strongest. It is already very dangerous on its own, but when combined with other toxic proteins, the effects become even more powerful on many vital systems and organs in the body. This makes the venom of the inland taipan one of the most dangerous natural toxins ever known. The story of this native taipan snake is the clearest evidence of the harshness and terror of the wild world. What do you think about the terrifying venom of this native Australian reptile? Please leave your opinion in the comments section.
Curious? Subscribe and step through the next anomaly.